Hello, everyone. So today we are going to continue talking about the CPM linear programming modeling. And today I'm going to provide you two problem sets. So we're gonna solve them together. So first, let me share my screen. Okay. Okay, so this is the first problem set. Okay, so we are given a list of activities and their immediate predecessors, the duration of each activity. So let's first draw an activity on arc network diagram. Okay, so while constructing the AOA diagram, we'll need to make sure two things. One, an activity should not be represented by more than one arc. And two, any two nodes in the network diagram cannot be connected by more than one arc, right? Okay, so in the network, AOA network diagram, so usually node 0 represents the start of the project, right? So I'm gonna have node 0 down here. And because these two tasks, A and B, has only one, okay, activity A has no predecessor. So an arc should lead from node 0 to activity A, which has no predecessors, right? So that's going to be activity A, okay? And all three activities, B, C, and D, has a predecessor, which is activity A. So I'm going to have one goes here. Let's say this is activity B. And then let's say this is activity C and activity D down here. Okay. And the next, E and F. Okay, E has a predecessor, which is C, and F has predecessor D. And then the following activity, G has three predecessors, B, E, F. Okay, so that's going to be easy, like this. We have E, F, and then that's going to be G like that. Okay. Okay, so this is what I made earlier. So now let's compute the earliest time. So I'm going to put the earliest time for each event. And then later, we're going to compute the latest time for each event. Okay, so let me change the color of pen. Okay, so the starting at time t equals 0, earliest time for the start node becomes 0, right? So we have 0 down here. So automatically the early start time for activity A is gonna be 0, right? And early finish time for activity A is going to be 0 plus the duration for its activity, which is 3. So it's going to be 3 down here. Right? And the event number 0 is the completion time of activity A, which is 3. So the earliest start time, earliest time for event number 1 is going to be 3. So the earliest start time for both activities C and D is going to be 3. 3 plus 7 becomes 10. 3 plus 4 becomes 7, right? And up here, earliest time for event number 2 becomes 10. So earliest start time for event activity 2 becomes 10, right? So down here, the earliest time for event number 3 is going to be 7. And 7 plus 4 becomes 11, right? And down here, okay, early start time for activity B is also going to be 3 from here, right? So 3 plus 5 becomes 8, right? Now we are ready to determine the earliest time for event number 4. That's gonna be the completion time for all 3 activities, E, B, and F, right? So, we didn't compute the early finish time for activity E. That's going to be 10 plus 2 is 12. So right now, we are going to choose the maximum value among these 3, 12, 8, and 11. So it's going to be 12 because event number 4 is the completion time of all 3 activities, E, B, and F, right? Okay. And then earliest finish time for activity G is going to be 12 plus 4, which is 16. So we know that the project can be completed within 16 weeks. Okay. Let me just disable my camera. Okay. Now we know the project can be completed in 16 weeks. So we know the latest time for event number 5 is going to be 16. Let me change the color of pen. So we have 16 down here. And then we're gonna work backward right now, right? So we have latest finish time for activity G is going to be 16 automatically, right? And then latest time for event number 4. Oh, I'm so sorry. I didn't compute the latest start time for activity G. That's going to be 16 minus 4, which is 12. So the latest time for event number 4 is going to be 12 from here, right? So automatically, the latest finish time for all 3 activities, E, B, and F, is going to be 12. So I have 12, 12, and 12, right? 12 minus 4, 8, 12 minus 5, 7, and 12 minus 2, 10. Some of you probably already noticed how the critical path looks like, right? Okay, so down here, The latest time for event number 3 is going to be 8. Up here, the latest time for event number 2 is going to be 10. So 10 minus 7 becomes 3, and 7, I'm sorry, it's going to be 8, right? 8 minus 4 becomes 4, right? Now we are ready to determine the latest time for event number 1. So that's going to be the smaller value between these two values, 3 and 4. So we are going to take 3. So 3 minus 3 becomes 0. And finally, the latest time for event number 0 becomes 0, right? Okay, now we are ready to determine the critical activities. And we've learned that any activities in the network diagram with a total float value of 0 is going to be a critical activities, right? So total float. The value of total flow is going to be the differences between these two values, right? Earliest start time and earliest, the latest start time for each activities, okay? And the path from the start node, which is node number 0, to the finish node, in our case, is node number 5, that consists entirely of the critical activities, is called a critical path. So in our case, critical path and critical activities. How does it look like then? So obviously, activity A is one of the critical activities, right? Because there is no differences between these two numbers. Same thing happens. Activity C is going to be one of other critical activities because there is no differences between these two numbers, right? 3 and 3. Likewise, activity E and G is going to be included in the critical activities. So it's going to be A, C, E, and G, right? Of course, the critical path going to be starting from 0, goes to 1, and then 2, and then 4, and then 5. So 0, 1, 2, 4, and 5. That's our critical path. Of course, we can complete the entire project within 16 weeks. Right? Okay, now let's set up an LP model that can be used to find the project critical path. And last time we learned that the dual LP can provide what you need, right? Although the primary LP can provide you the project completion time, it's not going to give you the detailed information about the critical activities and critical path, right? So let's build up our dual LP. Okay? So first of all, we need to define the decision variable for each directed arc, right? So if you remember, we defined X variable, X of ij, right? That is the unit flow. So unit flow from node I to node J. Okay. And the critical path in any project network is the longest path from the start node to the finish node. Our objective is to find the longest path. So we are going to maximize 3 times x01, right? And then 7 times x12. And then 4 times x13. 5 times x14. 2 times x24. 4 times x34. Then finally 4 times x45. That's our objective function. And we've learned that last time, the constraints of the dual LPs are the conservation of flow equations for this AOA network diagram. Okay. So the left-hand side of each constraint is going to be inflow minus outflow. So that the right-hand side value becomes the net flow amount. Okay. So if we are considering the supply node, then the net flow amount becomes negative value. On the other hand, if you are considering the demand node, so in our case, the finishing node, that's going to be the demanding node, then the net flow value is going to be positive. And all the other nodes, that's going to be 0 value, right? Okay, so let's do that. So for event number 0, there is no inflow, but there is one outflow that goes to event number 1. So no inflow, but there is one outflow, x01 is equal to -1. That's for event number 0, right? Likewise, for event number 1, there is one inflow, but there are 3 different outflow, right? So let's put them in here. So x01 minus, there are 3 outflows, x12, x13, x14, right? Is equal to 0. That's for event number 1, right? Next, for event number 2, we have one inflow and one outflow, right? So let me change the color. For event number 2, one inflow, x12, and one outflow, x24 is equal to 0 for event number 2, right? And for event number 3, we have one inflow and one outflow, right? So that's going to be x13 minus x34 is equal to 0 for event number 3. For event number 4, we have 3 inflows, 1, 2, and 3. And we have only one outflow, right? So x24, x14, x34, those are the inflows, and then one outflow, x45 is equal to 0 for event number 4. Finally, considering event number 5, we have only one inflow, but there is no outflow, right? So x45 is equal to 1 because node number 5 is a demanding node, right? Event number 5. All right? Of course, each variable x of ij is greater than or equal to 0 for every I and j values. Okay. So let's put them in our in the Lindo or Lingo model. So I'm gonna open Lingo. And just make sure if the opened window is for Lindo model or Lingo model, and it does say Lingo model. So let's use Lingo input then. So that's going to be max equals, right? 3x01 plus 7x12 plus 4x13 plus 5x14 plus 2x24, 4x34, and 4x45, right? Oh, and I forgot asterisk as the multiplication symbol. So let's put them in here. Okay. And then don't forget semicolon at the end of objective function. And our constraint set, the left-hand side value is going to be inflow minus outflow for each node, for each event, right? So that the right-hand side value becomes the net flow. For event number 0, that's going to be negative x01 equals negative 1. For event number 1, x01 minus x12, x13, x14, right? Equal to 0. For event number 2, x12 minus x24 equals 0. Event number 3, x13 minus x34 becomes 0. For event number 4, x24, x14, x34 minus x45 equals 0. Finally, event number 5, x45 equals 1. I think that's it. Okay, let's run it. Okay, so we've got the optimal solution. So that's the identical information, right? So Lingo tells you that the project can be completed as soon as 16 weeks, right? Which is same as we identified earlier. And the critical path, according to the Lingo, the critical path is going to be 0, 1, 2, 4, and 5, right? In a way, the critical activities include A, C, E, and G. All right? Okay. Now let's get back to our presentation slides. Okay, so this is our second example, second problem for today. So again, we are given a list of activities and the duration of each activities in a table like that. And this time, the precedence relationships are provided in a bulleted list like this. Okay, now let me give you about 10 to 15 minutes. Why don't you first construct an AOA network diagram based on this precedence relationship. So why don't you pause the lecture video and then come back whenever you are ready, okay? Okay, so this is what I've come up with earlier, AOA network diagram based on these precedence relationships. And I also put the duration of each activities on this AOA network diagram. Okay. And I believe we need only 3 dummy activities in this case. Here is one of them, and then second one, and the third one, like that. And one thing I'd like to mention at the moment is for any case, you better utilize the smaller number of dummy activities if possible. So if you utilize more dummy activities, what's going to happen is later it's going to have a negative impact on the size of your LP model, right? So just make sure your AOA network diagram uses the smaller number, I mean the minimum number of dummy activities if possible, okay? Okay, so let me change the color of my pen. Okay, so starting at time t equals 0, the earliest time for activity A and B and C, all three of them, the earliest start time is going to be 0, right? So I'm going to put 0. And then 0 plus 5 becomes 5. 0 plus 4 becomes 4. 0 plus 3, it's going to be 3, right? And the earliest time for event number 1 is going to be 4, because that's the completion time of activity 4, right? So automatically, again, earliest start time for activities D1, H, E, and F are going to be 4, right? Like that. 4 plus 0, 4, 4 plus 7, 11, 4 plus 6, 10, 4 plus 5, 9, right? Okay, now we are ready to determine the earliest time for event number 2. That's the completion time for both activities A and D1, dummy activity 1. So we are going to take the larger value between 3 and 4. So that's going to be 4 up here. So the earliest start time for activity D going to be 4. 4 plus 3, 7, right? And then we can get the earliest time for event number 3. That's going to be 11. 11 plus 0, 11, right? Now we are ready to determine earliest time for event number 4. So we are going to take the larger value between 11 and 10, which is 11 down here, right? So the earliest time for both activities, J and I, gonna be 11, right? 11 plus 4, 15. 11 plus 3, 14. And down here, we can determine the earliest time for event number 5. That's going to be the larger value between 5 and 9. So we have 9 down here. And then 9 plus 0, 9. 9 plus 4, 13. Like that, right? What else? Okay, now we move on to event number 6. And the earliest time for event number 6 gonna be largest value between 9, 15, and 7. So it's gonna be 15, right? And then 15 plus 1, 16, right? And 16, 16 plus 2, 18, right? Is that right? Okay. Now we are ready to determine the earliest time for event number 8. So again, we are going to go with the largest value between 18, 14, 13. So it's going to be 18. Is that right? Okay, now let me change the color. Since we know the project can be completed in 18 weeks, so we know the latest time for event number 8 is going to be 18, right? So the latest finish time for activities L, I, and G is going to be 18, right? So 18, 18, 18. 18 minus 4, 14. 18 minus 3, 15. 18 minus 2, 16. So we have 16 up here. 16 minus 1, 15, right? So we have 15. Since the latest time for event number 6 is 15, the latest finish time for all three activities, D, J, and dummy activity number 3 is going to be 15. So we have 15 and 15. 15 minus 3, 12. 15 minus 4, 11. 15 minus 0, 15, right? Now we are ready to determine the latest time for event number 5. This time we are going to choose the smaller value between these two, right? So 14 goes in there. And then 14 minus 5, 9. 14 minus 5, 9, right? And also we are ready to determine the latest time for event number 4, right? That's going to be the smaller value between 11 and 15. So we have 11 down here. So 11 minus 0, 11. 11 minus 6, so 5. Okay. And we have 11 up here. 11 minus 7. That's going to be 4, right? We cannot determine the latest time for event number 1 because we didn't do that for event number 2 yet. So first, you need to determine the latest time for event number 2. That's going to be 12 from here, right? And then we have 12 minus 0, 12. 12 minus 3, 9, right? Now we are ready to determine latest time for event number 0. So we are going to take the minimum value among these 4 values, 12, 4, 5, 9. So minimum occurs here at 4. And then 4 minus 4 becomes 0. Now we are ready for determining the latest time for event number 0. Again, we are going to choose the minimum value among these 3. So it's going to be 0. Okay, so now let's determine the critical path. So we need to get the total float for each activities, right? So what you need is compare the values between these two, right? For each activity, we need to compare the earliest start time and latest start time, right? If there is no differences, then the corresponding activity is going to be one of the critical activities, right? Just like this. Activity B would be one of the critical activities because there is no differences between these two numbers, right? Same thing happened here. Activity H and dummy activity 2, activity J, K, L, right? So if you make a connection from the start node to 1, 3, 4, 6, 7, and then 8. That's going to be the critical path. So I'm going to write it down here, critical path. gonna be 0, 1, 3, 4, 6, 7, and 8. The corresponding critical activities are going to be B, H, domain activity 2. You don't need to include that. And J. What did I do? Okay. J, K, and R, right? And the project completion time is going to be 18 weeks, right? So it's going to be 18 weeks. Okay, right? Now, let's build up the LP model to get the same information, critical paths, critical activities, and the project completion time, or at least project completion times, okay? So that's gonna be maximizing four times x01, right? And then 3 times x02. And 5 times x05, right? Zero times x12, 7 times x13, 6 times x14, 5 times x15, right? 3 times x26, 0 times x34, 4 times x46, 3 times x48, 0 times x56, 4 times x58, 1 times x67, and finally 2 times x2 times x78, right? That's our objective function. Constraint says for each event, left-hand side, it's going to be inflow minus outflow, so that the right-hand side becomes the net flow values, right? So for event number 0, there is no inflow, but we have 3 outflows, right? So that's going to be negative x01, x02, x05 is equal to negative 1, because event number 0, the node number 0 is the supply node. The net flow value has to be negative 1. And event number 1, we have 1 inflow, but there are 4 different outflows, right? So x01 minus x12, 13, 14, 15, right? It's equal to 0. Similarly, for event number 2, there are 2 inflows, but there is 1 outflow, right? x02, x12, right? Minus x26 equals 0. Event number 3, there is one inflow and one outflow, right? 1, 3 minus x 3, 4 from 0. Event number 4, there are 2 inflows and 2 outflows, right? x1, 4, 3, 4, right? Minus 4, 6, 4, 8, right? For event number 5, 2 inflows and 2 outflows, right? Okay, so x0, 5, x1, 5, minus x5, 6, x5, 8, 0. Now we move on to event number 6. There is 3 inflows, 1 outflow. So x2, 6, 4, 6, 5, 6, right? Minus x6, 7 equals 0. Event number 7, 1 inflow from node 6 and 1 outflow goes to node number 8. And event number 8, there are 3 inflows but no outflows, right? 4, 8, 5, 8, sorry, and 7, 8 equals 1, because event number 8, node number 8 is the demand node. The net flow value must be equal to 1. Okay. And all of the decision variable has non-negativity restriction for every I and j values. So putting together, this is the complete LP model. Okay. So again, let's put them in the lingo. I'm gonna open the new window, make sure, okay, so you're going to use lingo input again. So it's gonna be max 4x01, 3x02, 5x05, 7x13, 6x14, 5x15, 3x26, 4x46, 3x48, 4x58, x67, 2x78, and I'm gonna include asterisk as the multiplication symbol. Okay, and the constraint set, that's going to be negative x01 plus x02 plus x05 versus negative 1. x01 minus x12, x13, x14, x15 becomes 0. x02, x 2 minus x 26 equals 0. 1, 3 minus 3, 4 equals 0. X 1, 4, 3, 4 minus x 4, 6, 4, 8 equals 0. Okay. 0, 5, 1, 5 minus 5, 6, 5, 8 equals 0. This variable here. Okay. Now we move on to event number 6. So it has 3 inflows. 4, 6, 5, 6, and then 1 outflow. 6, 7. X 6, 7, 7, 8, 0. Okay, finally, event number 8 that has 3 inflows, X 4, 8, 5, 8, 7, 8, and there is no outflow. Okay, that's it. I hope I didn't make any errors. Okay, good. So we got the optimal solution. And let's compare with what we already identified earlier. So here, Lingo output tells us the project can be completed as soon as 18 weeks, right? Which is same as our previous result, right? And the Lingo input tells us the critical path should be 0, 1, right? Right here, 0, 1, 1, 3, 4, 6, 7, and 8, which is identical to what we've already identified, right? Down here, critical path is 0, 1, 3, 4, 6, 7, 8. In a way, we have P, H, J, K, R as the critical activities. Okay. So I think that's all for today. So next time, I'm going to talk about the crashing a project, and I believe we are gonna spend 1 more hour, and then move on to the new topic. Okay, thank you. As always, if you have any questions or concerns regarding this course, please feel free to reach out to me. Thank you. Okay, bye-bye.